We're going to look at how to convert recurring decimals to fractions and vice versa. We can convert recurring decimals to fractions because they're rational numbers, and basically we're going to look at the reverse process. So here we got 2.7451. We're going to show that it's a recurring decimal, and hence because it's a recurring decimal, we can show that it's integer over integer. We can write it as a fraction, and thus it's not irrational. Now, this is not a formal proof, but it is related to some of the work we've done so far on types of proofs. So that's why the word show is used. Alright, so not a formal proof, but it's got elements of proof in it. So let's make sure we understand that the number 2.7451, the recurring bar is only over the last three digits. So if we wrote that out in an expanded form, we have 2.7451, 451, 451. You get the picture. Alright, and what we need to do is quote unquote get rid of the recurring bits, which is the 451. So how many digits are recurring? Well, you can count to three, can't you? 451, 1, 2, 3, 1, 2, 3, 1, 2, 3. So there are three digits. So when there are three digits recurring, multiply it by 10 to the power 3, aka 1000. So we're also going to let x equal the number, this said number. So let x equal that 2.7451 with the recurring over the 451. So I said before multiply by 1000. So if x equals that 1000x equals, well, the decimal spot 1, 2, 3. So it's just sitting there after the 5 now. So 2, or another way of saying it, the numbers have shifted in reference to the decimal to the left. 2745.1, 451, 451 ad infinitum. So we put x there below it. So this is going to be a subtraction. So if we put x below it, keeping all of your values. Now this may be a tech-free question. Perhaps it's going to be on a tech-free exam. So you need to learn by hand methods sometimes. It also helps you understand things too. So let's do that subtraction. Well, 999x, that's pretty easy, and we need to do a subtraction. So if we do that, we get 2742.4, and note that the beauty of this is that these trios have a partner to dance with, and they're eliminated. Don't you hate my mixed metaphors? Alright, but basically eliminates the recurring part. Yay, that actually gives us some progress. So 999x is 2742.4. Now, integer, think integer. Okay, 999 is an integer. 2742.4 is not yet an integer, so let's multiply by 10 on both sides. 27424, and look, we were dealing with x before, and we still want to know what x is. We just want to know that it's integer over integer. Alright, so show that it's rational. means that both the top and the bottom are integers, and in fact I've just spotted some flaws in my question wording, so let me refine that question a little bit. How do you like that? Is that better? So show this recurring decimal in rational form, hence you're showing that it's not irrational, because there is a myth, isn't there? The myth is that anything recurring is irrational. Now that's not true. If there's some sort of recurring pattern, whether it's a straight away or eventually, that's not irrational. So we are looking at it, the recurring thing and the non-terminating thing need to be dealt with separately. Okay, so recurring is non-terminating, but irrational numbers are not terminating. The main thing is this recurring pattern is absent from irrational numbers. There's no discernible pattern. Anyway, back to the question. So to get x by itself, we simply rearrange and we get 27,424 over 9,990, which simplifies to 13,712 over 4,995 if we divide the top and bottom by 2. That's our answer. Okay, so we have put it in rational form. That's not irrational, that's an integer on the top and on the bottom. Okay, part 2. So let's do kind of the opposite now. We've got a rational number, rational form, and let's turn it into recurring decimal. So how do we do that? By hand. So the emphasis again is on by hand, tech free. Okay, so what we've got is 4 divided by 11. So 4, try again. 4 divided by 11. Now, because 4 is smaller than 11, I'm going to put some placeholders in there. And basically, it's a type of long division. You may have been shown in this way. Maybe you haven't. Maybe you've been shown not at all. Maybe you've been shown in a different way. But I'm going to show you this way. So, treating 4.0 a bit like 30, a bit like 40, I should say. I don't know why you would treat 4 like 30, it doesn't make sense. So treating 4.0 a bit like 40, if we had to fit 11 into 40, we'd say, well, we can do it 3 times in a bit. Well, we can do this 0.3 times. Because instead of 33, 3 times 11, we've got 3.3. We expect a value, of course, for the quotient to be less than 1. Okay, the result of division should be less than 1 because 4 is significantly less than 11, and we subtract, and we got 0.7. Some more placeholders. Yum, placeholders. Alright, so perhaps we should treat 0.70 like 70, and we would get 11 up to 66 if it was 70, but of course it's not. So it'd be times 600ths, and then we subtract again, and we get 0.04. Okay, and we keep repeating. So if we treat 0.40 as 40, we could get up to 33, but of course that's not 33. It's way smaller than that. It's 0.033, so we haven't times by 3, we've times by 3,000ths. Okay, subtract again. Gee, when will we get to the end of this? Well, you know something already, don't you? If you don't know, you haven't been paying attention. So pay attention. So we've got this, we're stuck in an infinite loop. So look, placeholder, yum. So we've got that there, and look, this thing keeps repeating. Good, because it's supposed to. Okay, so basically you can see that this is going to generate, so it's going to keep generate 3636. So the quotient, writing it down, properly, the quotient is 0.36 recurring.